So I've now begun to solve problems using Newton's second law. And I understand that one of the challenges of solving Newton's second law problems is understanding the net force. On the left-hand side of Newton's second law, it says that the sum of all the forces is equal to the mass times the acceleration. So a critical thing is to be able to look at a physical situation and be able to divine from your experience or your training the variety of forces that can affect the motion of an object and the directions in which they act. It can be a significant challenge. In fact, it's where all the physics happens in solving Newton's second law type problem. So in order to facilitate that, I created a list of forces that I might encounter in honors physics. And that list of forces goes the weight force, push-pull force, tension, as in the force exerted by a rope, normal force, friction, spring force. Those are the forces that I consider in my honors physics. When I talked about the weight force, I said that there's an equation that I can use to calculate how much weight there is in a given situation. It's really easy to do. The weight of a thing is its mass multiplied by g, 9.8 meters per second squared, which is the acceleration that's caused by gravity near the surface of the Earth. So it's an equation for weight. But the other forces on my list, they don't have equations associated with them, except when I described the friction force to you on that list, I suggested out loud that there was an equation that could be used to calculate how much friction force you expect to encounter in a given physical situation. But I wasn't going to get into it right then because I didn't want to overcomplicate what I was talking about. Well, now, the time has come to investigate the frictional force and see if it's possible, and indeed it is, for me to devise an equation that I can use to determine how much frictional force I should expect in any given problem that I'm solving. In a problem that I solved in the previous lecture, I had a crate being dragged along a factory floor. And I simply said that there was 20 newtons of friction force. How did I know that? Well, when I'm writing problems, I have godlike powers. I can make the friction force anything I like. But now I'd like to know, how could I know that in advance, that it's an appropriate amount of friction for the situation I'm looking at? The friction force. Everyone in the room already knows quite a bit about the nature of the frictional force. That's because the frictional force plays a role in just about everything that happens in our everyday lives. Friction forces occur whenever any two material surfaces come in contact with each other and move relative to each other or experience other external forces relative to each other. Friction is the force that occurs when surfaces come in contact and rub laterally along the surface of contact. The reason why I specify is that there's another force of contact between surfaces, and that is the normal force. When I solved problems of projectile motion, I broke the velocity down into two components. The vertical velocity, which would be the y-axis velocity, and the x velocity. When I started applying Newton's second law, I recognized it's a vector equation, and so that I might break forces down into y-axis forces and x-axis forces. Well, when two surfaces come in contact, there are really two components of force. The component of force that is perpendicular to the surface, which I've already identified, is the normal force. And the component of force that is parallel to the surface, that force is the friction. In all the years I've been doing this, I was searching around for a definition of friction force that I liked, something that I could tell students they could write down in their notes. In every textbook I looked in, I didn't really find a satisfactory answer, and so I invented my own. The friction force is the force that opposes the relative motion of surfaces. The friction force is the force that opposes relative motion of surface. And this is a force that you already have experience with in your everyday lives. Indeed, when I'm drawing free body diagrams, I can ask the audience, which way do you think the friction force acts? Because you understand in a general sort of way that the friction tends to resist the relative motion of two surfaces. If two surfaces are in contact and not sliding relative to each other, the friction force is going to tend to prevent them from sliding. If two surfaces are sliding relative to each other, the friction is going to tend to stop them from sliding. I encompass that whole idea in saying that the friction force is the force that opposes the relative motion. If they are moving relative, tries to stop it. If they're not moving, tries to keep them from not moving. But now, I want to devise an equation. So to devise an equation, I'm going to do it in the context of an experiment. For the purpose of my experiment, I have this lead brick here. It's made of lead. It's quite heavy. Everyone picks it up, says, it's so much heavier than it looks. Yeah, it's lead. It's extraordinarily dense. So this lead block, I'm going to sit on the table here, and this is my experimental instance of friction. I've chosen the lead brick because I knew, based on experience, that when I set it down here, there'd be quite a bit of friction for me to investigate. It wouldn't make sense for me to put down something that was very slippery, because if I put down something that's very slippery, then it would be difficult for me to observe the friction. But there's a lot of friction here. So I'm going to do an experiment to investigate this, and the first thing that I want to do is to understand the nature of the forces that act on the brick. So I'll draw a free body diagram. Here I'll just draw a box that represents the brick, and I'll draw on it all of the forces that I believe influence the motion of the brick. All of the forces that I believe influence the motion of the brick. Well, does the brick have weight? Most certainly it does, and that weight, mg, is directed downward. And so I draw a vector downward that is the weight, the mass times the acceleration due to gravity. Is anybody pushing or pulling on the brick? Well, here's how the experiment's going to go. I'll come over here, and with my hand, I'll push on the brick to the right with a certain amount of force horizontal to the table. So is anybody pushing on the brick? Yeah, me, in this experiment. So on my free body diagram, I'm going to draw a force directed to the right that is my push force. And I'll just call that force F, the force that I exert on the brick. It's me pushing. Any ropes attached? No. Any surfaces in contact? Yes. The block is in contact with the table. Friction is all about the interaction between two objects whose surfaces are in contact. If the brick were not touching the table, then there would be no frictional interaction. So it's touching the table, so there's a force of contact. And that force of contact is the normal force. It is perpendicular to the surface in contact. The surface of the table is horizontal, so perpendicular is straight up. Now imagine that I'm unaware that friction exists. Don't know anything about it. Not even expecting it. A curious thing happens when I perform my experiment, because here I see that my free body diagram indicates that my push force is the only force that acts horizontally. So when I push on the brick, what I expect, according to Newton's second law, is that the brick should accelerate under the influence of my force. But the brick doesn't accelerate. I need to be able to explain the absence of motion of the brick when I push on it. There must be some other force acting that opposes the force that I apply, and that force opposing my applied force is the force of friction, the force that I now seek to understand. Where does friction come from? Well, I had mentioned before that when I use a rope to exert a force, I tie a rope to a thing and I pull, that if I look deeply at the rope, really what's going on is that the rope is made of molecules. And those molecules exert electrodynamic forces on each other, and that's really where the force of the rope comes from. I just generalize the force as a tension because I don't really think it helps me at all to go into all the bother of figuring out all those little molecular interactions. And indeed, I can solve problems without knowing all the details. Well, when the brick sits on the table here, if I zoom in with my mind to the interaction between the bottom of the brick and the top of the table is composed of molecules, and the brick composed of molecules. And those molecules exert electrodynamic forces upon each other in the same way that the intermolecular forces inside of a rope create the tension force. Those forces have two components. A component that is perpendicular to the table. It's why the block doesn't just fall through the table. That is the normal force. But there's another component. There's a sideways component. There's a component of force that is parallel to the surface of the table. That is the friction force and its interaction between the molecules. Now, I don't understand all of those molecular details that are going on between the block and the table, but I don't need to, because I immediately make a curious observation. If I don't exert any force, that is, if my push force here, F, is equal to 0, then the block does its inertial thing. It just sits there and it doesn't go anywhere. If I don't apply a force, it just sits there. That's nice. That's inertial behavior, an object at rest tending to stay at rest. If I exert a force, say 1 Newton of force, there I am pushing with 1 Newton. Charlie, how do you know you're pushing with 1 Newton? Well, yeah, I'm just using my finger. but I have sort of magical powers to understand these things. I know when I'm pushing with exactly 1 newton, but that's just a fake. I could get a computer in here and a probe and a data recording device and get a little piezo, like a force sensor, and calibrate the thing and do a whole sciencey thing so I know how many newtons of force that I'm pushing with. When I push with 1 newton of force, the block doesn't move, which means the friction force must be 1 newton of force. But if I push with 2 newtons of force, the block still doesn't move. That means that the friction force must be 2 newtons of force. If I press with 5 newtons of force, the block still doesn't move. That means the friction force must be 5 newtons of force. Now that's just an idea I'm getting from observation here, but I can quantify it by writing out Newton's second law. Newton's second law tells me that the sum of the forces is equal to the mass times the acceleration. That's Newton's second law in general. Notice I left the harpoon off because by now I understand that Newton's second law is a vector law and that forces have directions and the directions matter. At the moment, I really don't have any interest in the vertical application of Newton's second law in this problem. I'm only interested in the horizontal application. So I'll look at my free body diagram and consider the horizontal forces that act on the block. I have the force that I push with, which is a positive force, presuming that I choose to the right to be the positive direction. I think you can see I naturally would do that. The positive force on the brick and the negative force of friction, which opposes that force, is equal to the mass times the acceleration. But an observation that I'm making in my experiment here is that the acceleration of the block is equal to 0. It just sits there. It doesn't do anything. It just sits there. It doesn't do anything. And as a result, the force that I apply, which I can measure how many newtons that is, must be equal to the friction force that is opposing the motion of the block. So in a sense, I don't measure the friction force directly, but I measure the force that I apply, and I realize, according to Newton's second law, that the force that I apply is equal to the friction force. And now I'm going to make a graph of the friction force that I observe as a function of how hard I push on the brick. So the friction force as a function of my push force. And hopefully you furrow your brow at that. That's weird. Why make that graph? That graph is obvious. Because I determined experimentally, just an observation I did now, that if I push with 1 newton of force, the friction force is 1 newton of force. 2, 3, 4, 5 newtons of force I push with, the friction force always responds. And so this graph is a straight line with a slope of 1, because every time I push with an extra newton, the friction force increases by an extra newton, and the friction force that I get always responds. First of all, we can't use the word energy in this context. Energy is kind of a protected word. We have an entire unit of physics later on for energy. But what you mean is that when I push harder, something happens on the molecular level that causes the molecular force to get stronger. And it really has to do with distance. Electromagnetic force, like gravity, depends on the distance. So when I push on the block effectively, right, I'm not being very specific here, it's sort of a vague idea. When I push on the block, I'm pushing the molecules against each other harder, so that, like a spring, not exactly like a spring, but like a spring, as I press on it, it gets stiffer and stiffer and stiffer and stiffer and stiffer. So what I propose from this experimental observation is that I push, and 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 however hard I push, the friction force responds, right? Except, if I push hard enough, increasing my force, stronger and stronger and stronger and stronger and stronger, if I push hard enough, I can get the block to slip. If I push hard enough, I can get the friction to give up and allow the block to slide. Now, that's a little bit more difficult to understand, but remember, I can measure how much force I'm exerting. And this is what I discovered. That the force increases until it reaches a certain maximum value. And we can do all kinds of experiments to figure out how many newtons that maximum value is. But there always is one. There's a limit to it. I reach that maximum value and then it slips. After it slips, this is what my graph looks like. The friction force precipitously drops. And after that point, when it's slipping, no matter how hard I push, the friction force does not increase. Friction is more sophisticated than I might have realized. But if you think about it, you already knew this. Because you can imagine a situation where I have a large thing here, maybe it's a refrigerator or something, and I begin to push on it, and I'm trying to push it, but I can't make it slide. Why? Because the friction force between the object and the floor is too great. I can't overcome it. So I say, Megan, would you help me? And you come up. And together we push. More force now, and we can get over that, and whammo, it starts to slide. And then I say thank you, and you stop pushing, and now that you helped me get it going, now I can push it by myself, right? I think from your life experience, that story sounds reasonable. I just needed help to get it started. And then once I get it started, it's easier to push. Notice that this level of force here is lower than the maximum force when it's not sliding. Why should this be? Well, again, the molecular interactions between material substances when they're in contact with each other are very, very complicated. But visualize it like this. The fingers of my left hand here, 1, 2, 3, 4, are the molecules of the table. The fingers of my right hand, 1, 2, 3, 4, are the molecules of the block. And when the block sits on the table, the molecules sit in proximity to each other. And if I try to move my fingers side to side, they're locked in. And you can see the harder I push, the harder it pushes back. Locked in. But if I push hard enough, the separation between my fingers will actually increase and they slip. Once they slip, there is less force impeding the motion. Now, that's not a very exact idea, but I think it's a fair illustration of how once the molecular interaction is broken, that it can slide freely thereafter. So the friction force I discover is rather complicated in the sense that it has a dual nature. Friction behaves differently when surfaces are not sliding. We call that static friction. The friction when objects are not sliding relative to each other is called static friction. When they are sliding relative to each other, we call that kinetic friction. And these words work really well for me because I know that the word static means stationary and the word kinetic means moving. So the static frictional force is the frictional force when two surfaces are not sliding relative to each other, and the kinetic frictional force is the force when they are sliding relative to each other and they're not the same. Friction has a dual nature. So when I devise an equation for friction, I'm going to certainly have to take that fact into account. So now there are some things that I understand about friction. Friction is parallel to the surfaces in contact. It's caused by a molecular interaction. It opposes the relative motion of surfaces if they're not moving relative to each other. It tries to prevent the motion. And if they are moving relative to others, it starts to stop the motion. It comes in two kinds, static and kinetic friction. Now, I would like to devise an equation for friction. That is, I would very much like to be able to write an equation that says the friction is equal to. Because if I could write that equation, then I can calculate how much friction I expect in a given set of physical circumstances. So, the question is, what does friction depend on? What does friction depend on? That's the question that I have. Another way of phrasing that question is, if I have a given circumstance where there's some friction, for example, between the block and the table, or any other instance of friction that you can think of. When I have an instance of friction, how could I increase the amount of friction under a given circumstance? How could I increase the friction between the block and the table? Do you want to have a go? Make the surfaces rougher. That is, change the materials that are involved. Because different materials have different molecular structure. And make it rougher, right? Like make it physically rougher. My claim would be, in the context of how I'm talking about it, if I take this surface and I sandblast it to make it rougher, I've changed the material. So comparing a smooth surface to a rough surface is the same as comparing a plastic surface to a rubber surface. They have different structure and therefore apply different amounts of force. And a good example of that is if I decide that I would like to play basketball. To be successful at basketball, I need to provide large acceleration because my competitors are going to be playing against me. And in order to be successful at it, I have to be able to change my velocity rapidly. Change of velocity over time is acceleration. In order to be successful at basketball, I need large acceleration. To have large acceleration, I need large force. So I do not play basketball in my dress shoes. Catastrophe. Even walking on a basketball court in dress shoes is difficult because the smooth leather, the bottom of a men's dress shoe, on the waxed floor of the basketball court is a very low friction situation. So I put on basketball shoes by virtue of the fact that the basketball shoes are made of rubber, and indeed, scientists spend a little bit of time thinking about exactly how to cook the rubber up so the friction is greater. A little aside from my own life, I like to go out into the mountains and hike around places and whatnot. And I bought a pair of hiking boots, and of course they're advertising them to me, so that all kinds of wonderful features that they have. Temperatures where they promise me my feet will stay warm. Depths of water where they'll be waterproof and my feet won't get wet. But another one on the list was super high friction rubber sole. And I was like, sure, it's super high friction, because they're making physics claims, and I'm going to be a little bit careful about that. So I put these boots on, and then I find myself trudging through the forest, and there are rocks covered in moss with water flowing over them. That is a low friction situation. You step on it, wing, you go flying. So with my new fancy boots, I step out on the rock, super friction boots. I was ever so excited. Somehow they had found a way to manufacture the rubber of the boots in such a way that the friction was very large, just by materials. So maybe I should play basketball in my hiking boots. It's not going to make any difference because, I know this question's on your mind, no, I cannot dunk. I'm not terribly sure that I could even grab the rim. So basketball's not my thing, so hiking boots wouldn't make much of a difference. Maybe ice skating is more my thing. I don't know. I've never ice skated. I think that would be calamitous. And in the age of viral videos, I don't think anybody wants to see that. But if I go ice skating, I put skates on with metal blades on ice. And the reason why I do that is when I'm ice skating, I don't want high friction. I want low friction. I want to push off and glide across the ice with a very low acceleration. Nearly zero, but not completely zero. That's impossible. But a very low acceleration. So rubber on waxed hardwood is high friction. Steel on ice is low friction because the amount of friction that I get depends on materials. Because friction depends on molecular structure, fine structure of the material. Well, I said I'm not going to worry about all the details of electrodynamic forces between materials. So what I do instead is I say that the force of friction is proportional to the frictioniness of the materials. That doesn't sound very sciencey, the frictioniness of materials. I probably should have a more scientific name for that. Mu. It's a Greek letter. When I write a mu, it's a little fancier than the typeset mu. If you go in your word processing software and type out a mu, the stick on the end of it is usually straight. I give mine a little flair. The Greek letter mu is known as the coefficient of friction. Now, regrettably sometimes, you have students of physics who are not paying really careful attention. Mu is the coefficient of friction. It is not the friction itself. The coefficient of friction is not friction. It is literally only part of the equation. Every once in a while, someone who's giving a talk will say, it is only part of the equation. They could be talking about anything. But in this case, literally. The coefficient of friction is only part of the equation. It only gives me part of the proportionality of the friction force. The coefficient of friction is a number that describes the frictioniness of the materials in any given situation, whether it's rubber on waxed hardwood, or steel on ice, or rubber on asphalt as a car tries to skid to a stop. All of these situations have different coefficients of friction. The coefficient of friction is generally a number less than 1. So if I'm solving a problem, I would not be surprised to see a coefficient of friction that is 0.8. That would be a relatively high coefficient of friction. Or to see a coefficient of friction of 0.2, that would be a relatively low coefficient of friction. It's possible for coefficient of friction to be greater than 1, but if that occurs, probably the problem is not that realistic. Now, anytime I introduce a new quantity, it's important that I describe the units in which that quantity is measured. So I hope you'll appreciate what I mean when I draw a square bracket for the units and write no units inside. The coefficient of friction is a dimensionless quantity. It does not have units. It does not have units. There are many dimensionless quantities in physics, so it's no surprise to me, but it's the first one that we've encountered in our physics. And so I wanted to make a clear point of that. So the coefficient of friction describes the type of materials, but that is not the only thing that friction depends on. So now, using the same materials, how in a given physical situation could I increase the amount of friction? How in a given situation where there's friction, could I increase the amount of friction? It depends on more than one thing. You're going to hit it again? So you think that if I push down on this thing, Well, what if, because there's two kinds of friction. There's moving friction and not moving friction. So static friction. Okay, I'm going to give you the confidence. You are completely right. How about that? Friction force is a force of contact. So how much friction force I get depends on how hard I squeeze the two surfaces together. You can easily demonstrate it for yourself. So if you take your hands and you gently rub them together, there's a little bit of friction between. You squeeze your hands together more firmly, the friction increases. And indeed, as you rub your hand across the table, if you push down harder, it increases the friction. That's why if you're trying to scrub a mess off, right? If you want to get more friction to clean up a mess, you exert more downward force, your sponge or whatever. And I'm really glad that you said it that way, because the most common answer to that is to increase the weight of a thing. The idea being, if the brick weighed more, there would be more friction. And indeed, in my example, I said a refrigerator. I chose a refrigerator because a refrigerator weighs a lot, and so I expect there'd be more friction. But here's why. Look at my free body diagram again, where I previously ignored the vertical forces that act. Now, consider them, please. The normal force directed upward, the weight force directed downward. In this free body diagram, since the vertical acceleration is equal to 0, that means that the normal force upward is equal to the weight downward. In this problem, not in all problems, in this problem, the normal force is equal to the weight. So if I increase the weight of the thing in this problem, I increase the force of the surfaces being pressed together, because I've mislaid my marker. Because the friction force is also proportional to the normal force, the force of contact in between. In the previous lecture, I had solved a problem of a crate being dragged along a factory floor, and the force exerted on the crate was at an angle. And I had worked out what the normal force was, but when I solved that problem, I said, well, I don't really care about the vertical forces here, but I could find the normal force. So I did an equation, and I figured out that the normal force was equal to whatever that happened to be. Actually, no, it was mg minus t sine theta, but that's not important. I found out what the normal force was, but at that time I said, who cares? I'm not interested in that. I want to find the horizontal acceleration thing. I don't need to know the normal force. Well, now, when I'm solving problems, the normal force is interesting to me. I want to know it, because along with the coefficient of friction, the normal force helps me calculate the force of friction, which is the coefficient of friction multiplied by the normal force. This is the equation that I was seeking the whole time. The equation that allows me to calculate how much frictional force I can expect in any given situation. Yeah, Charlie, but then you got to know mu. You got to know the coefficient of friction for different circumstances in order to use this equation. Yeah, sure. Which is why scientists have done experiments to figure out the coefficient of friction between every material substance and every other one that you could possibly imagine. And they write them all down in a big book and put it up on a shelf, because at some point, someone's going to be doing some kind of sciencey thing where there's friction, and they'll need to know. Or an engineer will be building a machine or something with moving parts, and they want to know, what is this kind of rubber against this kind of steel, and how much friction can I expect? And that coefficient of friction has been experimentally determined. So for you, the student of physics, very commonly, you'll be told what the coefficient of friction is in the problem. It'll say the coefficient of friction is 0.5. And the reason why you're being told is because you need the coefficient of friction to calculate the friction force. But that's not all. You'll be given a coefficient of friction, and you'll have to go shopping for the normal force. That is, you'll have to write out Newton's second law to determine what the normal force is. And then the coefficient of friction multiplied by the normal force, that'll give you the friction force. I have my equation for friction force. Yay! Trouble is, I'm not done yet, because I haven't handled the fact that there are two different kinds of friction. Static friction, where two surfaces are not sliding relative to each other, and kinetic friction, where they do slide relative to each other. I need to have that in my physics. I need to understand that. Well, it turns out all I have to do is really appreciate that idea. I don't have to change my equation much at all. But there are two kinds of friction. And the way that I handle that is I'll just make two different coefficients of friction. I'll make a coefficient of friction for the static case, that is when surfaces are not sliding relative to each other, and I'll call that mu static, or mu sub s, as I've written here. And I'll create a coefficient of friction for the kinetic case, and I'll call that mu sub k, mu kinetic. Static friction coefficient and kinetic friction coefficient. And often, as a problem solver, You'll read the problem statement and it'll tell you both. It'll tell you what they both are. And you say, Shadi, which one am I supposed to use? Well, that's part of the question. If the surfaces are not sliding, you use the static. If they are sliding, you use the kinetic. I can write a physics problem where at first things are not sliding and then they are, in which case you would change which coefficient you're using. There's a feature to my experimental graph here that the maximum static frictional force is larger than the kinetic frictional force. In general, static friction is greater than kinetic friction in general. And so what I'll observe is that the static friction coefficient is always greater than the kinetic friction coefficient. That way, my static frictional force, my maximum static frictional force, is always greater than the kinetic frictional force for the same materials under the same physical circumstances. Now, once I have two different coefficients of friction, I can just go ahead and use this equation. Just make sure you're using the right coefficient of friction. A little bit of detail. When it comes to static friction, the static friction could be zero. I started my experiment with the brick just sitting on the table. I'm not exerting any force, and therefore friction is not exerting any force. And so the static frictional force is equal to zero, and then increases to some maximum static frictional force. That's on my graph here, where the static frictional force starts at zero and goes to a maximum value. And that maximum static frictional force is mu static times the normal force. So a little bit of care is taken in appreciating the fact that if I calculate mu static times n, I have only found the maximum static frictional. In a lot of physical situations, the static frictional force will be whatever it needs to be in order to stop the motion from happening. When it comes to kinetic friction, there's only one value for the kinetic frictional force, and that is kinetic frictional force is equal to mu kinetic, the kinetic coefficient of friction, multiplied by the normal force. So now, my procedure for solving Newton's second law problems has not changed. I still draw a picture, choose coordinates, draw a free body diagram showing all of the forces that act, write Newton's second law for all coordinate directions, and then solve. But now, I have an equation for the force of friction. So my understanding of that force becomes a little bit more sophisticated, and I'll just include that in my problem solving. And that allows me to solve much more interesting problems.